Okay, so today we're going to cover the charging system. All right, just to kind of give you a feel for what we're going to be doing in the charging system, I kind of broke it out where these components are on the vehicle itself. The first thing we're going to do is the at-home charging section. So we're going to have there's a little box that we got up here, the cable box itself that interfaces to the car and then to your plug at the house. And then the module itself is number one. It's actually in the right front corner of the vehicle. Then the other module we're going to cover is the high current DC to low current DC, basically the one that replaces the alternator. That one's located in the trunk of the vehicle. And then the last portion of it, or the other part we're actually going to cover in the middle, is going to be the inverter converter. It's the one that drives the actual motors and the transmission and actually provides the regenerative charging back to the battery. And that's located inside the engine compartment, right where the number 3 is up there. And it's right at the back of the engine assembly itself. So let's kind of looking at the view, the same things I was just telling you about. The right front corner up there is the inverter converter. The left top corner is the AC to DC charging unit. So when you're plugged in at home, that's the one that's converting the electricity there. And then the one at the bottom is the DC, or the one in the middle is DC to DC for the one that's replacing the alternator. And then, of course, we've got the cable assembly itself.
Hi, I'm John Scott Thomas, and I'm from UBM TechInsights, and I'm the analog and control circuit guy. This is called a charging talk. It's really a little bit more than that. We're going to talk about how the energy is moved from the energy sources into the vehicle and then ultimately to the electronics and the wheels of the car. So if you were here yesterday and you look at this block diagram of the power system, what we talked about was the lithium-ion battery. And I'll just give you a very brief review of what it is. This battery pack pumps out 360 volts of energy. It holds 16 kilowatt hours of energy entirely, and it uses 10 kilowatt hours, or 65% of its total capacity. The pack is made by LG Chem, and it's manufactured in Brownstown, Michigan, and it uses a lithium-ion chemistry, much like the Tesla system. It uses a lithium manganese spinel cathode, which can hold a considerable amount of power, and they're probably going to migrate that over the next year to a new type of chemistry. So how does the power get from this lithium-ion battery pack to the wheels? Down here. And how does the power get from the grid, when you plug it in and you go home to your garage, into the battery pack? So one of the things about the Chevy Volt is that in order to supplement the battery pack and remove range anxiety, which is the psychological fear and physical reality that you will run out of power after about 30 or distance about 35 miles into your trip, they've put on board a gas engine. So that gas engine can work in harmony with the lithium-ion battery pack to extend the range of the vehicle. Without that, you'd be limited to about 35 miles of range. With that, you can get a standard range of about 300 to 360 miles on a tank of gas plus a full charge. And what we're going to talk about here is the way the energy from the gas engine and the lithium-ion battery pack combine to drive the wheels. We're going to go through these yellowish components and the electronics on board, and we're going to see how these things, which are basically sophisticated circuits, take the energy and move it into these green electromechanical units, which transfer electrical energy into mechanical energy that drive the wheels. And there's a lot of stuff going on here, and I think the one thing I want to convey during this presentation is the complexity of the control systems that are required to make it all work. And you should get a sense of that as we get a little bit deeper into that. Now, I'm going to take you through basically step by step or component by component what some of these things do. The first one is the AC to DC converter. Its job is to take line voltage, which can be either 110 volt standard outlet or 240 volts if you get installed in your garage a special converter that GM provides. And it takes that AC voltage, converts it to DC, and then steps it up to a voltage that's large enough to provide the 360 volts that can then feed into the lithium-ion battery pack and the rest of the vehicle to charge up the battery pack and provide power. So that's the first thing we're going to look at, the AC to DC converter. The next thing we're going to examine is something called the inverter. This is the most complex piece of electronics in the system. Its job is to take the DC voltage from the battery pack and then convert that into an AC voltage that can drive electric motors that are on board. There's two electric motors used in the system. The main one is the traction motor. The traction motor is the one that connects the AC voltage feeding out from the inverter. It's a three-phase voltage. It comes in there, and it has a total of peak 149 horsepower output, which is fairly considerable. And I took one out for a test drive last week, and one of the really nice things about this car is that it really accelerates very quietly, much faster than a gas engine. It's a nice thing to drive. And when you get up to speeds of 60 or 70 or 80 miles per hour, I tried it on the freeway back home, it really holds its own. It's not a weak or a wussy type of feel. You can get a lot of power out of the traction motor. So this AC voltage, of course, has characteristics that have to be tightly controlled in order to drive the traction motor successfully. It has to control the phase and the amount of current driving into the motor in order to get the proper power transfer to the wheel system. The generator motor, its primary function is to be driven by the gas engine, and it generates electricity that can feed back through the inverter. So this inverter can go backwards as well, and then pump out DC voltage back into the battery pack. Now you'll see also that there are some interesting arrows down here and also over here. This generator motor has the ability to transfer power to the wheels, and we'll talk about that in a few minutes, and also to recover energy from the wheels. The process called regenerative braking, when the vehicle is slowing down, can take the wheel energy, the kinetic energy of the car, and then convert that using a traction motor and the generator motor and going through the inverter into the lithium-ion battery pack. Gas engine itself is a 1.4 liter, 63 horsepower output. It burns premium gas. The reason for doing that is that it uses a high compression ratio to run efficiently. GM says they can get about a 10% to 15% efficiency improvement by using premium gas. There's a 12-gallon gas tank in the back of the vehicle. All right, so I think we've talked enough about this. I want to say one more thing, which is that this gas is really designed to be supplementary for extended trips. If you are driving it locally, most of the time the gas engine never has to turn on. So if you're commuting back and forth between work and you're charging it at night, you can go for months without using the gasoline engine. Jay Leno, who has a Chevy Volt, drove it for 10,000 miles without having to fill up his gas tank. So when that happens, you get into the interesting situation where the engine and the gas can start to stagnate, and the car has to know how to deal with that. The first thing it will do, if you've gone for a couple of weeks without using the gas engine, it will tell you, hey, run down the battery, get the gas engine to turn on. And if you don't do that, after another set period of time, it will actually run the gas engine in maintenance mode just to get the fluids in the gas engine circulating. So a lot of people in their daily commute will never have to use this component. All right. I think I'll say a quick note about the cooling loops, although it's not really central, again, to get across this idea of the sophisticated control. As I said yesterday, there are 4 separate cooling loops required by this car. One cooling loop is used for the battery, where the temperature maintenance and regulation is critical, and it can cool or heat the battery as required to keep it at approximately room temperature. Another cooling loop is used for the inverter, which burns a lot of juice when it's running, and also cools the AC to DC converter, which is a little surprising because that can burn fairly hot during the charging process. You get another cooling loop for the gas engine and then the passenger compartment. And then finally, the 4th loop is used to control the transaxle, this mechanical unit down here, and cool both traction motor and generator motor. So you have 4 loops of fluid circulating through this car, and they're all regulated and they're all controlled with 4 separate pump systems as required to keep this vehicle operating in the proper mode.
We're going to start with the home charging system. Well, when you purchase a car, GM provides you what they call the home charging cable here. So basically, it's a 110 plug. It does require a ground fault. If it doesn't have a ground fault, it's not going to charge. So that is one of the requirements of it. Everybody always wants to know what's inside these things, so you got to open them up and rip them apart. One of the nice things about my job is I never have to put anything back together. So what's nice about it, though, is they vibration welded it together. You see the pieces falling out. But it's basically a plastic housing, vibration welded together. There was 2 circuit boards residing inside of this. We'll go ahead and pass that around. So you can basically see the cable here. That's the power cable coming in, and then you got the main cord here for the power, that you plug into the car. It also has a couple of LED lights on the front of it. One of the boards is set in here, then the other board was on the back side. So this is basically what you would start, what you're going to plug into at your home. And then, John, when we pulled these modules out, what'd you find on them?
First of all, I wanted to show this slide. This is what you would see if you had this in your garage hanging. A couple of lights indicating that the unit is on, and when you're actually powering, there are little LEDs that come on inside the vehicle. But what I want to emphasize here is that middle set, or lower set of green LEDs, and the orange button. And what this thing is doing here is it's setting the peak amount of power that can be sent to the vehicle. And by pressing that orange button, you change the peak power that can be transmitted. And the reason for that is that people can run into the situation where the circuit in your house, pumping out 120 volts, can't handle the power needed to charge up the vehicle. So if that's the case, you press this orange button, and it reduces the peak power transfer so that hopefully you're not continually tripping your circuit breaker as you're charging your car up. This brings up an interesting contrast and something I would like to hear more about with the Tesla approach to this. So if you heard about the Model S this morning, one of the statements that was made was that there will be this mode where you can charge it in half an hour up to the point where you can drive 150 miles. That's a very interesting comment. I'm really curious to see how Tesla approaches that, because it typically takes for 120 volts about 12 hours to charge up the car. That'll get you 35 miles, so a fraction of what the Tesla Model S will be able to do. And even with a 240 volt dedicated supply, it takes 3 to 4 hours, again, getting only 35 miles. So this is a really heavy demand. Even if the vehicle itself, the Model S, is capable of doing that, the circuitry that will be required to provide that rate of charging will be extreme. So when they said that, I was quite intrigued, and we'll see when they release the vehicle whether they're doing that with dedicated stations or they have something else up their sleeve. But certainly the approach with the Chevy Volt right now doesn't allow that level of rapid charging, and you have to actually control it rather carefully so you don't start tripping circuits all over the place. Now, at the board level, these are relatively simple boards. In here, the power comes in. On the right-hand side, you've got 240 volts coming in on the right-hand side. Sorry, I apologize. On the left-hand side, it's transferred through a series of relays. There's a piggyback board that generates plus or minus 15 volts for basic electronics. And then on the right-hand side, it goes into the vehicle. And the only thing really of note electrically is that large inductor, which we think is a current sensor. So you can't pump too much current through this whole system and end up melting wires. The piggyback board is down below. It's got some LEDs, surface mount LEDs on it. And it's Lear Corporation who makes this particular system. And they've made several others in the vehicle that we'll see.
Okay, so now we're going to talk about the charging system that's on the vehicle. We passed around the cable itself. Well, now guess what has to happen? The vehicle's got to drag this big module that you see up here. It's going to be in the right front corner, and it weighed about 10, 15 pounds. I'm going to wander over the vehicle, and we're going to videotape it here as we go along. Now, this module is liquid cooled at all times. It does have a coolant loop running through it. So basically what happens is you have that big orange cable I passed around. It has to plug into this side of the car right here. From there, they actually have cabling that routes through the inside of the vehicle and comes over here to this right front corner. So when we get to that right front corner, we might be able to find where that module was located. So that module was located down here in this corner. Now, what seems strange to me is I plug it in on the left side, I got the module on the right side. Well, guess what? Over here was an engine controller. My engine's on this side. Now, you could summarize or you could theorize why would they do that? Well, one of the things with vehicle manufacturers, they have to do an offset crash. In that offset crash, they try to reduce the amount of cost, too, for insurance purposes. Typically, cars would get hit in the left front corner. I put the expensive module in the right front corner, so when you get in a crash, you don't have to worry about the insurance claim of replacing that expensive module. All they have over there is their engine control module, which they make every day, and they use it across multiple vehicles. Now, as you look down in here, you'll see the large orange cables for your high current coming in. You see you have your coolant loops. So they do have coolant coming in, and then you have other little connector here for one of the sensors. So there's really not a whole lot coming down into this corner. So, John, when you pulled that module apart, if you want to switch back to the presentation and just show us what you found inside that.
Sure. So when we take the AC to DC module and pop the lid on it, what we see is something that looks like this. If anybody here is into power electronics, there's lots of great stuff going on. Along the bottom of the image, there's 4 inputs and outputs. The orange ones are the 360-volt input or output of this module that goes to the battery pack. And then the 120 and 240-volt input comes through that big brown EMI filter. Delta's the name of the manufacturer. Got lots of great big capacitors there, and what happens is that AC voltage is rectified to create a quasi-DC voltage, and the capacitors smooth that out. You've got some interference chokes that protect against EMI. Up on the top, the 2 green connectors are control units, and on the lower left, it's worth noting those are capacitors, but what GM has done is taken a lot of care throughout the manufacture of these power components to isolate them from vibration and so on. So you can see yellow mylar tape over many of the components throughout the design, and then a lot of the time they use sort of a goop, a white goop, I'm not really sure what it is, but they stabilize the components from vibration. This is sitting right on the front of the car, so it's moving around quite a bit, getting exposed to a lot of things, wind vibration and so on. And of course, over the lifetime of a car, you can get fatigue in the metals, so they really tape and glue everything down to make this a nice, stable, long-lived design.
Yeah, John, they usually use a lot of silicone adhesives in automotive to help hold those components in, as you mentioned, with the vibration side of things, especially when you get in the engine compartments.
And we'll see more about that, too. Okay, thanks, Al. And then you have the other thing to note on this is down at the bottom again, you have 2 pipes, and those are the coolant input and output. So if you could strip all this stuff off out of this module, you would see a great big coolant loop. And on the back side, what we have here is the power is now in this DC state, and it's transferred to the back side of the module, and then it goes through something called a switched converter, which uses great big, I think I have a picture of it here, actually. There it is. Yep, so that's just flipping the module over and taking a look at it. Switch converters use great big inductors and great big capacitors, and switching field effect transistors, or IGBTs. Looks like they're FETs in this case. I'm not sure, actually. But the thing to note here is those big gray rectangles, and we thought that was quite unusual. What those rectangles are magnets, and so those magnets are part of a transformer structure. It's used in the switching converter. And what's notable about this is that the windings for the transformers are actually embedded in the PCB. So if you could take one of those gray magnet systems out, it's like a clamp that fits around the PCB, and the windings are embedded in there, which is an interesting way of doing it because copper wire can carry a lot more current. We figured that they did it to mechanically stabilize this module because of the environment that it's in, rather than using just pure copper windings. Now, the inverter.
Okay, so now we're going to move back to the inverter. If you want to, we'll just talk to the slides real quick, and then we'll switch to the cam. At this point, you're looking at the back side is where all the high current cables are. You got the 2 AC, the 3-phase AC coming in on the side there, And then at the very back, there's 2 high current DC cables that are connected to the module. So, and then if you look at the very front of this inverter, there's a couple of 40-pin connectors in there. One of the interesting things that I found as I was researching, one of the things we did is we got a subscription to GM Service Manual, but there's basically 7 different serial communication lines coming into this module. So basically, it looks like this module is communicating to all the other hybrid modules that are located in the vehicle. Some of the other inputs in the front of that is that you got your typical 12 volts, your powers and grounds, for communications there. It also has 2 coolant connections right there at the front of that module. So now we're going to look at where that module resides in the vehicle. It's basically sitting right here on top of the transmission. One of the things that I found that was interesting was I had to pull this cover off, and when I pulled this cover off, there's actually a circuit disconnect right here on top of it. So usually when you have a beauty cover, you don't connect electronics to it. So you have to, so why would they do that? Well, the thing is, all your high current circuits in this vehicle have circuit disconnects, with the exception of the ones to the converter. So what they did is they eliminated basically 5 different circuit disconnects and integrated it into a single one here. So when you pull this cover off, it basically disables the entire high current system in the vehicle so that the operator or the mechanic doesn't have to worry about electrocution or anything. So when you get down inside here and you look, you'll see you got the 3-phase cables going down to the transmission. And then you also have the 2 here for the high current. Now, one of the things about this, you try to assemble it, when you think about assembling these are very large cables. So what they do is they use nuts on the backs or a bolt on it, and so they just basically run it down because you have a high insertion force, so you have to be able to overcome that. So they just use a couple of fasteners to run those down. So you got those 2 on the back, you got the 3 here, and then you also have one on the front, which is for an auxiliary pump cable is what it's called out. And then you have, of course, you have a couple of cam locks here for all your 40-pin IOs. And then it just basically bolts down inside of there.
All right. So that was the inverter. Just to remind you where we're at in the powertrain, there it is, front and center of the whole system. This is the brain, or as close as we can get to the brain of the vehicle. What it's doing is it's taking power from the battery and from the gas engine, as we will see, and converting it to the wheel system through these 2 motors. So it has to do a lot of stuff, and it has to be very clever. We're going to take a look at the 4 different drive modes that the Chevy Volt can use to propel the vehicle. And I think you're going to find this pretty interesting. I certainly find it, it's very sophisticated. And let's just march through the 4 quickly here. This is the one where you're going to do 90% of your driving if you're commuting. What happens here? Your battery's charged up. You've got a fully charged battery. You come out in the morning. Power comes out into the inverter. The inverter converts it to 3-phase AC, and it goes through the traction motor, this big electric motor, and that goes directly in here to this drive unit that turns the wheels, okay? Now, that's the way you use this when you're running in a purely electric mode, and the hope is that you will spend most of your time running in that. You'll notice here that these arrows have two heads on them, one going in and one going backwards. So power can actually flow from the wheels through this transaxle unit or drive unit, back through the traction motor, up through the inverter, and then back in. That's a process called regenerative braking, trying to recover that kinetic energy of the vehicle, get a little bit more mileage out. As I mentioned yesterday, this battery pack holds approximately the equivalent of 1 gallon of gasoline. So they're really careful about energy harvesting and using that equivalent of a gallon of gas, trying to get as much back as they possibly can. We'll see that in the other drive modes as well. They figure that if they do it right with this regenerative braking, you can approximately, for city driving, recover maybe 10% of the power and get 10% more out of a fully charged battery. So in the traction-only mode, the most common mode, you have a fairly simple arrangement. This is the next one. What's going on here is that you're now running the traction motor at a fairly high speed. This is when you're on the highway, you're going fast, 70 or 80 miles an hour. And what happens at this point is that the traction motor that's going through this is spinning too fast to really be efficient. So it gets less and less efficient the faster it goes. So what GM does to get around this is they then kick in the generator motor. You'll notice that there's no gas engine up here. That's been disconnected from the powertrain. There's a clutching system that can control how everything connects up. So the generator motor is spinning. Additionally, the traction motor is turning, and what that does is it allows both motors to turn closer to the most efficient RPM rate. Okay? And they say typically you can get an extra couple of kilometers out of a battery pack by doing this. So this gives you a sense of how careful they are. A couple of kilometers is not very much, but they still have to put this in place. Okay, so that's the second mode. The third mode kicks in when your battery pack is dropped down below about 30% of its full charge. That's the threshold. GM tries to not fully deplete the lithium-ion battery pack. They keep it to a middle range. And the reason for that is to extend the durability of the battery pack as much as possible. It has a 10-year warranty on it. They figure it's good for about 5,000 charge cycles compared to your toothbrush, which can do 300 to 500 charge cycles. They really need to get a lot out of this battery pack, okay? So when it gets down below about 30% of the fully charged value, the gasoline engine turns on. And what it does is it starts spinning the generator motor. So you'll now see that a clutch has engaged these two components, and another clutch has disengaged the generator motor from the drive unit. So you're now running power down through here, backwards up through the inverter, and at that point you can distribute power to the traction motor to drive the vehicle. You can also recharge your battery. The fourth one is the most controversial one. This is where the discussion of whether this is an electric vehicle or a hybrid vehicle comes in. This is when you're really trying to go fast, and again, the clutch re-engages here between the generator motor and the transaxle unit. So you now have a direct mechanical linkage between the gas engine and the wheels. So by definition, I would say this is probably best called a hybrid vehicle, although GM likes to call it an electrical vehicle. To control all of these systems, the clutches, the coolants, the motors, how they're engaged, what's going on with regenerative braking, how power is being transferred, the inverter has a total of 4 microcontrollers on it. The largest one, number one, is the supervisory controller. We're going to take a look at that. The next microcontroller we'll be looking at is the traction motor controller. The third microprocessor is the generator motor to run that generator, to couple the gas engine to the rest of the system. And then finally, the clutches are controlled and the transmission through another independent microcontroller. So this is the board right here. And all I'm going to emphasize right now is there they all are, all 4 of them. You can see the supervisory controller is the largest. The other guys are a little bit smaller here. The control, the clutch, generator, traction motor. And then there's supporting electronics around that. What we do, we always like to look inside the silicon at our company and see what's going on at that level. So when we pop the lid off of this one, we stick it in a bath of hot acid, basically, to remove the package. And this is what we saw. We've got a big block of standard cell logic. That's where all the digital functionality is performed. Then a very large flash memory, 3 megabytes. Largest memory we have found so far on this vehicle. That's for all that sophisticated control that has to take place. And what this is, it's a Freescale 32-bit Cariva embedded controller running on 3.3 volts, a few other details with an analog to digital converter. And I think for our final talk here, we've got 1 minute left, we're going to take a look at the DC to DC converter. And all this guy does is it takes the high voltage of 360 volts and converts it to 12-volt standard operating DC for the rest of the vehicle.
Okay, so this module is located in the trunk, and we're going to show where it's at, but since we're running short on time, it's basically a die-cast aluminum housing, and then if you see the black part underneath, it's actually an injection molded duct, and they actually run air. There's a pump in the back or a fan in the very back of the vehicle. They actually air cool this module because as those FETs are changing and converting, the currents and that, you build up heat and they got to dissipate it. So this one's actually air cooled. One of the other interesting things about this module is if you look in that top where I got the red box up there, there's actually a piece of security tape. They don't want anybody to go into this module. Well, I don't look at little things like that. I don't let that deter me.
So this is it. And all this thing does is it takes 360 volts, uses a switching converter, turns it into 12 volts, and it tries to do that efficiently, of course. So you've got on this side here your large voltage coming in, a nice input filter with heavy-duty wiring coming through your switching system here, Underneath you, again, you can see an interesting control system, an inductor, another one of these inductors embedded in the PCB. On top is the control board. Renaissance has that socket, so it's a Renaissance microcontroller. And as Al said, it's air-cooled, and the manufacturer of the system is TDK.
Probably one of the biggest things that you'll find within this vehicle is the very last comment, or last bullet that you see there. The diversity of the suppliers. You have Lear, you have TDK, you've got Hitachi. So now they got to tie all these boxes together in their communication. It's all got to fall within the GM architecture for communication. But they're trying to get all these suppliers to all communicate to each other. So it really is bringing a lot of different suppliers into this vehicle. And we'll see it again tomorrow, and we saw it yesterday with the LG and so on.
That's right.
I believe we want, Brian, you want to...
Just if I could say on that point, I think I want to contrast that with the Tesla talk this morning, where there was this interesting comment how Tesla is trying to insource as much technology as possible. And then he went on to say that Detroit outsources a lot of their work, and maybe that's a bad thing. Good or bad, I don't know, but it seems to be true. You look at the number of companies manufacturing the components and where they're made. The inverter's made in Kentucky, the TDK and Lear's made in Detroit, and so they're made all over the place by many different companies. GM is obviously taking that approach with this vehicle, so it's an interesting contrast in approaches to design and manufacture.
It looks like we've run out of time here on Teardown Day 2. Thank you, Al, and thank you, John. That was another BOFO presentation, and tomorrow we'll be back at an earlier time, 11 a.m. We'll talk about the infotainment system. You're not going to want to miss that as well. So thank you for your patience and your interest. And if you want to follow us on the road, it's driveforoinnovation.com.